So today we are very, very happy to have Madhu Sudan from Harvard visiting us. I think almost all of us can think about at least one result of Madhu's that you associate with or are reminded by. So today I think Madhu is going to tell us about something completely different, something that he's been doing, I guess, in the last couple of years, which is like new generalizations of sparsification and the cool connections that come out. So Madhu, take it away.
Hey, great. Thanks for having me here, Pravesh. You can still see the indentation in the chair where Avi used to sit. So, I guess I have to say, it's great to be here immediately after Avi gets the Turing Award. And it's a pity that he left town just to avoid me. But I hope he sees the video. All right, this is joint work today with Sanjeev Khanna, who's the pen, and Louis Petterman, who's sitting in the back over here. Louis is responsible for much of the work over here, and I see some in the room. So if you have questions, you can definitely ask him. All right, so I'm not an expert by far in this concept called sparsification, and I suspect some of you actually know even less than me about it. So for you, I will explain to you where I think of sparsification as sitting. So the way I think of sparsification, it's something that sits between two concepts that we are hopefully more familiar with: compression and lossy compression. So what is compression? Compression is you have some big amount of data, you want to compress it in such a way that eventually you should be able to completely decompress it back to the original string. So if you have any questions to ask about the original data, you can still answer them with the complete compression because you can actually decompress it back to the original string, and now all the information is available. Lossy compression or noisy compression is something which is studied very commonly in the signal processing community and so on. It's a very deep and extensive study. It's called sort of rate distortion theory and so on. And I don't know everything about it, but roughly this is how I'd capture it. So you have some big string, you want to compress it so that when you decompress it, you don't get the original string, but something close to it. Now, which measure of distance you use is very important, but just as a toy example, let's say we were to compress with Hamming distance. What does that do for us? You can answer some questions about the original data, like what is this particular bit of the original data from 1 to n, which of these bits, what is this value of this bit? And you're not guaranteed that you will get this bit right, but for most of the bits, you'll get it right. Okay, so you're asked polynomially many questions about the data, in fact, linearly many questions. And you get the answer correctly to most of them, and you have no guarantee on any one particular bit, but most of them you will be fine. So on the one extreme, any question can be answered, compression. On the other extreme, a small number of questions can be answered mostly correct. But if you're doing compression, you might as well ask the question, what is it that I'm hoping to get back from this data after the compression? And sparsification more or less asks this question the right way. It says, I have this data. I know the class of questions that I'm going to ask. How well can I compress it? Okay. So this is a very natural question in this setting. And this is the class of things that I'm going to answer. And today, this is kind of what sparsification has usually been studied with. You will usually have a class of questions. Each one of these questions is going to be a real valued number, a positive real value, a non-negative real valued number. And what you would like to know is a 1 plus or minus epsilon approximation to that real valued number. And now we're going to say every one of these questions that I'm going to ask, I want the answer correctly to within this 1 plus or minus epsilon. And the interesting phenomena happens when the number of questions is super polynomial. If not, I would just write down a table of values for all of these questions. Or, maybe there are other things one could do. So the more completion questions happen when the number of questions that you're conceiving of asking is huge, but you still are able to compress. Yes, that.
So the specification has to be smaller, that you're trying to optimize the size of it, because it's smaller.
Exactly. So you're starting with some string X, which is big. You want to compress it into something smaller. And the question is, how much smaller can this new thing be relative to the old thing? Now, when it comes to compression and lossy compression, you have to define some measures of information saying, this is how much information is there in this model, etc. Today, we're going to be asking, once you specify the class of questions that you're asking, you can be pretty much worst case with respect to your thing. So there's going to be no distribution from which the strings are coming from. So can you do any compression whatsoever? And the remarkable thing, and this is the starting point of pretty much all the work on sparsification, I think, work of Karger from the late 90s, and then Benczur and Karger gave us this wonderful theorem: any graph on n vertices. So notice a graph on n vertices is roughly given by n square bits of information. For each pair of vertices, I have to tell you whether that edge is present or not. It can be compressed to roughly n bits up to some polylogarithmic factors, and today we'll be ignoring polylogarithmic factors, can be compressed to roughly n bits while answering one exponential class of queries accurately. What is the class of queries? I give you a cut in the graph, a partition of the vertex set into two sets, and I'll show you approximately how many edges are crossing this cut. Okay, so this is the way I want to view sparsification. Now, the way Benczur and Karger sparsified this original graph, and the way most of our results will work today, is not only do you actually say there is some way of writing order of n bits, the order of n bits will be actually corresponding to, or O tilde of n bits, they will actually correspond to a subgraph of the original graph with that many edges and weights on these edges. Okay, so I'll just tell you, okay, here is a subset of edges in the original graph with the following weighting scheme. And now if you just ask the same questions that you wanted to ask about the big graph, the small graph will have the same answers up to this 1 plus or minus epsilon factor. Okay. That's the theorem. That's the theorem that we want to talk about and extend today. And one of the beautiful ingredients in this result, and we'll talk more about it later, is this beautiful result of Karger. This is the engine that drives all of sparsification, at least the combinatorial results there, is this beautiful cut counting bound, which says that in a graph of minimum cut value C, whatever's the number C, if you ask how many cuts have value at most 10 times C, it's some polynomial in the number of vertices, okay? This lemma is key, and as we'll see a little bit more about this later. One thing that implies immediately is that if you take this graph and sample all the edges down by a factor of C, you will still preserve all the cut sizes exactly. You can take a union bound over all the cuts in the graph. Sampling this many edges is good enough. This lemma is actually good enough to prove even the theorem above, but that took a while. We have a simple proof today that we might actually see. By the way, most of the proofs that I'll be interested in showing are basically of the theorems on this page. I'll state other theorems and maybe talk about them, but if I don't get to those, it's okay by me. All right, so, and if you know this theorem and its proof, then maybe this is a good time to leave. All right, so, but yeah, so we do have some original work. So what is the original work? So, you know, we can ask what else can be sparsified, and as specified earlier, what else should be defined in terms of what's the data and what are the kinds of queries you want to answer about this data. And there's an extensive collection of things. Anything in blue is a name of a field which talks about sparsification. And there, the red part says exactly how you would formalize this in this context. Things that people have sparsified are what's called graph Laplacians, which is sort of, there's an associated quadratic form with any graph, and let's approximate every query related to that quadratic form. There's also this notion of a hypergraph cut sparsifier. So a hypergraph is edges are hyperedges. And now you would like to answer questions of the form, how many hyperedges cross a given cut? Now, when it comes to a graph, when you ask the question, how many edges cross a given cut, there's only one notion of what you could mean by crossing. Okay? One endpoint on each side. When it comes to a hyperedge, you could define crossing in many ways. The question that is asked usually in this hypergraph cut sparsification world is how many cuts have at least one vertex on each side. But you could ask, you know, how many cuts have at least two vertices on each side, or an odd number of vertices on one side, or, you know, a host of things. If you decide to ask these host of questions, then you will read into a land which I would call CSP sparsification. For every edge, I also could give a predicate saying, given a bipartition, is this actually split? Or I could consider tripartitions of the graph and say, okay, how many cuts have exactly one vertex in each color class? All of these questions would fall under this framework of CSP sparsification. And this is one of the target spaces that we will talk about today. What can you do when it comes to CSP sparsification? One special case in this space, which sort of sits over here, is when I say, an edge crosses a cut if an odd number of vertices is on the left side. Okay, so that would be called what we'll call XOR SAT sparsification. Up until this point, everything was known to have nearly linear sparsifications before our work. CSP sparsification is just a whole lot of questions, and it was answered up to the point that it was answered above. And one example that was left open at the end was this question saying, does this have linear size sparsifications? One of the answers that we give is that, yes, this also does have linear sparsification.
So, Madhu,
Yes.
You are not assuming any bound on the uniformity of the hypergraph here. Like it could be arbitrarily large at the moment.
Yes, and in particular, when we talk about CSP sparsification, typically you assume that there's some constant bound on the size of the constraint. Otherwise, it's not a uniform class. You want to specify the family, so you have to have a finite thing. When it comes to some non-uniformly specifiable thing where you say, look, my constraints are all XORs or all ORs, etc. Yeah, we're not assuming any bound on the thing. Our results apply to the case where things are unbounded. Yeah.
If your clauses are just linear equations over a finite field that's known, sparsify.
Very good question. So that's exactly the starting point of our work. So we said we call it code sparsification, but what's a code for us? It's a linear subspace over some finite field, maybe. Okay. Maybe over the reals also. And actually, I don't know if we ever do. We don't talk about the reals. So you think of the data here as the generator matrix of a code. So for me, a code is going to be like a tall, thin matrix. Each column is a code word, and any linear combination of the columns is a code word. Okay. So I'm given a very tall and thin matrix, which generates some code. And what are the code words? Code words are given by, when I multiply this by some vector, that's a code word. This is the message, and this gives me some code word. What I'd like to know is for each message, how many zeros and how many non-zero entries are here. Okay, approximately. Why would you ask this question? Actually, we didn't know why we should ask this question when we started this work. We just said, okay, look, this is, when you put Sanjeev and me in the same room, this is what happens. Okay, we just get some unreal questions. And a starting point was the realization that you could think of a cut sparsification in this language. A graph is given by an m by n matrix, m rows and n columns, m corresponding to the number of edges and n corresponding to the number of vertices. And you just think of each of these rows as representing the incidence of an edge, which are the two vertices that it touches. And if you do all your arithmetic over GF2, then when you multiply this, you get exactly the set of edges which cross a cut. And a 0, 1 vector that you're multiplying with corresponds to a cut. And multiplying this with this vector gives you exactly which edges are crossing the cut. So counting the number of non-zero entries is like counting the values of a cut. So Karger tells you that if you do this with matrices which have at most 2 ones per row, and you're doing the arithmetic over GF2, then everything is good. Okay. Now the generalization is quite clear. Can you do this over other matrices and other things? But other than the fact that it's encoding this one problem, initially we were not sure why else we would do it, but then we got some positive results, and then we were able to find a lot of very nice examples. Many of them are due to Louis. So one thing that we realized quickly is that this actually generalizes hypergraph sparsification. Okay. If you have a hyperedge, you just work over a very large field, prime field, let's say, and represent vertices on the hyperedge by sort of plus ones in a few coordinates, and in the last coordinate put a minus, if it's a hyperedge of size r, plus ones in r-1 coordinates and a minus r-1 in the last coordinate. The only way these numbers are going to sum to 0 is if you have sort of, I don't know. I forget. I mean, sorry. Oh, if this number sums to 0, it's because you have all the vertices on the same side of the cut. Any other partition will lead to a non-zero sum. So hypergraph sparsification had already been noticed as a challenging situation to extend Karger. People were doing a lot of careful work over here, and they did get sparsifications in the past, but this, if it works, will give us the cleanest proof that we know that hypergraphs are sparsifiable. So this is the question that we ask: codes, can they be sparsified? Later, we generalized this question because we needed it to generally additive spaces over groups. And if I get a chance, I'll explain what that is. And this immediately leads to lots of other related problems. You can actually show various CSP sparsification results. There are also some results about how you can create sparsifications of Cayley graphs by other Cayley graphs and so on. So spectral sparsifiers even, etc. So lots of cool results follow from this thing.
So the queries are also always 0, 1?
The queries are basically whatever is the message space. So you say, I give you a code word. How do you specify code word? You say, okay, I specify the message. What do I want to multiply this generator matrix by? And for that message, I'll tell you roughly how many non-zero coordinates are there in the output.
So it has to work for every query?
It has to work for every query.
Every query.
Every query. Okay. So yeah, sparsification, you usually say, I specify the set of queries and every query has to be answered approximately correctly. So the first result is that every linear code can be sparsified to basically the minimum number of possible things. It translates to k-square widths if you view it in the most sort of basic way, but the equivalent way of looking at it is that you can pick roughly k rows of this matrix. So you get a k by k matrix, and that matrix with the right weighting will tell you exactly how many code, what the weight of each code word is. Okay. So the number of columns remains the same. So the message space is this preserved, but the new code and with the weighting of these different coordinates will tell you exactly how many non-zero entries are there in each row. Okay. So, and this result, if you are willing to forgive polylog factors, is a strict, strictly subsuming Karger's result. So that's the way you want to think of it. I mean, up to the polylog factors, this is really, this captures Karger's result, but extends it to all linear spaces. And if you don't, in some cases, we were actually interested in doing this over Z mod M for some non-prime M. And that also works. So you can actually define, you can define any, consider any linear map from the integers, k-dimensional integer to n group elements. This is a kind of a very natural way of thinking about it. Group elements can be added to each other. So this, you can think of the inner product of an integer vector with a vector over the groups. And this can also be sparsified. I won't talk about this theorem much, except that, yeah, I mean, once you have this kind of a result, it's a natural extension to want this. And this is an important extension that allows us to talk about to get some characterizations. And you can even extend it to degree T polynomials, which map the same domain to this range. And when you do degree T polynomials, your sparsification size goes from k to the t, and k to the t is roughly the right amount. Yeah.
So the fact that there's z there shouldn't matter because it's you're actually looking at a finite number of queries.
Yeah, I mean the number of queries is finite because you're right that it. So the number of queries is infinite, but you're going to go mod G, but G need not be finite either. This result actually, as I stated it, is for a finite group. What do we do? Okay, so there's some, okay, so this, let's leave it. Yeah, let's imagine the group is finite for this theorem. That's the best way to look at it. And there are some extensions that are conceivable, even the group is infinite, but then some other things have to be restricted about the encoding function. So yeah.
If you look at like 0, 1 messages, but real value encoding, that would work.
0, 1 messages and real things, it would work. You would have to do some, I'm not totally sure exactly how well it will work. We've thought about what happens when the group is infinite, but then we were considering it in the CSP setting, and where it somehow turned out that looking at, there were really a finite number of possible things that we wanted to look at. Yeah. Yeah, I wouldn't make both of these infinite, and then I don't know what happens. All right, so the theorem as stated here is correct. The extensions to the infinite group case, they're not included here clearly, because this would be an infinite size thing. And there are some issues as to what it should be. Okay, so immediately once we have these things, there are lots of consequences to the CSP sparsification. And I won't say much about this except to say that, yeah, I mean, this was something that people had been looking at. And now we are starting to get lots of new positive results saying this CSP can be sparsified, that one can be sparsified, where things were not known. The most notable example was where all the constraints were XORs of variables. That's clearly captured by our setting and was not previously known to be sparsifiable to nearly linear size. But you can get all kinds of other results over here. So there are things, if your CSP can capture things like the AND of many variables, then it's not very sparsifiable. If the CSP can be expressed as the zeros of some low degree polynomial, then it is very sparsifiable compared to the degree of the polynomial. And results along this line tell us, for example, that, so if I have a symmetric CSP, which is, pretty much all hypergraph sparsification, any instance you think of hypergraph sparsification, it should be symmetric. I mean, whether I say, an odd number of variables or an even number of variables or at least 2 on each side, these are all symmetric constraints. They don't care, that the first vertex should be on the left and the second should be on the right. It's just how many variables are on each side. All of those we can tell you, exactly which subset of these are sparsifiable to nearly linear size and which ones are not. There is a kind of a, if the places where the constraint is not satisfied are sitting inside an arithmetic progression, then it's not sparsifiable. Then it is sparsifiable, and if not, it's not. So there's a very exact characterization of what things are sparsifiable. I guess, did I say this here in this? Yeah, if they don't, yeah. If you look at all the things which are not satisfying the predicate, they should be forming an arithmetic progression. Shouldn't be. All right. So lots of results. I think the proofs are going to tell us more about what we want to do. Sure. Yeah.
Could I ask a question?
Yes. Yeah.
Do XOR constraints fall in this class?
Yes. XOR constraints are so it's one of the nicest examples of an arithmetic progression. You have all the unsatisfying assignments are 1 modulo 2. The weight of an unsatisfying assignment is 1 modulo 2.
So we change by 2, like the common difference is
the common difference is 2, exactly. And in general, it will be of the form A mod B for some A and B. If the unsatisfying assignments are of the form A mod B, then you can sparsify it. If it's anything else, you will need at least quadratic size to sparsify it. Question?
Just curious, have you explored connections of this stuff to differential privacy?
And not really. Why do you ask?
Right, so in differential privacy, you have some database where the rows are indexed by users. And one of the basic things that they do there is subsample the rows to create a synthetic database. And then they try to argue that this synthetic database could answer some set of queries.
Yeah, that's a pretty nice, that's a nice question. We haven't thought about it. And I mean, the one thing that might be not so good about our result is that we actually take a subset of the actual users rather than create some synthetic ones. But that might be very feasible to do also, so that the sparsifier actually is not representing any of the rows. This may be actually a negative thing. In sparsification, we are saying take a subset of the people and let them be the samples. Maybe we would want a slightly different result, but it sits in the framework of sparsification. It's a very nice question. Yeah, Rob.
This theorem 4, it's only for 3 area predicates, or does it?
Theorem 4 is unfortunately, sorry. Theorem 4, okay, the if and only if part is only for 3 area predicates.
But for
The negative result that if it has a projection to and is just for all the things. But we don't get a classification for 4 array predicates at this stage. We don't know. And one of the things at the end of this sequence of results, the only sparsification we know for anything that looks like a CSP is based on this theorem from the previous page. Okay, based on this theorem 3. Okay, these are the only sparsifications we know. And on the other hand, the only impossibility for sparsification we know is because of this projection to and. If you contain an and, then you cannot be sparsified. And these two do not match, this much we know. But we don't know what happens in between. That is just like, yeah.
In a relationship to results in puncturing codes, like the puncturing of Reed-Miller, that's also,
So good. Good. So this is a sparsification when applied to coding theory is usually studied in the language of puncturing. You have a big code, you want to puncture it. But usually puncturing, we try to say, let's preserve the minimum distance. So the weight of the minimum weight code word, or, let it not become much worse. But here we are really saying, preserve the weight of every code word. So the task is a little bit more, needless, let's say, in the sense of, the interesting questions in sparsifications are the most uninteresting questions in coding theory. And we'll see a reason for it in a little while, in a few slides. But so coding theorists really should not have asked this question, and they did not. It's actually turning out to be a very nice way of looking at sparsification in the non-coding theory settings.
So minimum weight code word basically corresponds to value preservation. Is it like, I could have asked the version of the question where I don't care about the behavior on all assignments. I just care about whether the optimum is preserved.
Right. So, and we ask that question a lot. Can we just preserve the optimum? In general, when we preserve the optimum, we not only preserve the optimum, we also preserve the message which leads to the optimum, the solution that leads to the optimum. When you take a big code and you puncture it randomly, you say, well, why is the minimum weight preserved? Because take the minimum weight guy there and look, we would have sampled it the right number of times here. So we do rely on property which looks like sparsification, but then once you have kind of high enough weights, we don't care about it anymore. And this one cares about it. Good. Any other questions? Is the task clear? Yeah.
So have you also tried to explore like non-random specifications or like to do random?
Okay, good. Few things. Yeah, no, we have not explored, deterministic algorithms for sparsification. Should be conceivable. And actually, when we first wrote this paper, and I gave talks on this thing, one of the most interesting open questions was, how do you make this algorithmic? So all our results were actually existential. Now, actually, all our results are algorithmic. So unfortunately, one open question is gone from my slides. But I have 2 extra slides to compensate for that. All right, so that said, now we're going to talk about proofs of some of these results. We're going to start with the proof of sparsification because that's illustrative, that's what we need. Also, in this proof of sparsification, we sort of found sort of a nice way of even describing previous sparsification results, or capturing them or obtaining them. That's useful for us later, but even if you only care about graph sparsification, maybe an interesting thing to pay attention to. So the first thing you might ask is, okay, I have a big graph. I want to sample some, maintain a sparse sample of the edges, it's a random sample. That should work, right? But this example typically doesn't work because if you take a random sample of the edges of this graph, it's very unlikely you will capture this one edge. And if you don't pick that sample at one edge, then as far as you know, the size of this cut is 0. And 1 is not a 1 plus minus epsilon approximation to 0. So that's the problem. We can always get good additive approximations by sampling random subsets, but they work poorly when it comes to small cuts. And this is why Karger came up with his, or well, actually, this is not why he came up with his cut counting bound. He came up with this beautiful algorithm for finding minimum cuts in graphs, then observed later that, oh, this actually helps me count the number of small cuts in a graph. And then observed that if you can count the number of small cuts in a graph, random sampling actually works. Okay, so this is the order in which the works happen. I was alive in those days and saw these results. Each one of these is just amazing. Okay, so here is the proof. So what do we want to prove? That the number of cuts of size, like 10 times the minimum cut size in a graph, is polynomially bounded. So the 10 is this alpha, C is the size of the cut, M is the number of vertices and edges in the graph, and N is the number of vertices. What's Karger's algorithm to find a small cut in a graph? He just starts with this graph, picks a random edge and contracts it, meaning collapses the two end points. If you create multiple copies of edges between two vertices, you preserve multiple copies, you don't unify them. So you're going to create a multi-graph with self-loops and all in this process. Go ahead. Keep doing this till you're left with two vertices. These two vertices represent a bipartition of your original graph because some things got collapsed into the left and some other things got collapsed into the right. All the edges going from left to right are. Now here's what he's going to say. Fix some cut in this graph, one set which partitions this thing, which has, let's say, alpha times C edges. This algorithm is going to produce that cut without knowing it with noticeable probability, with probability n to the minus alpha. If this is producing this particular cut with probability n to the minus alpha, the number of cuts must be at most reciprocal of this probability. It's at most n to the alpha. And why is that the case? Well, if you fix some edge, which is, when you're left with, say, I vertices and you're looking at this graph, it still has a minimum cut of size C. You started off, the minimum cut was size at least C. It's still at least C. Okay. So the cut that you're looking at has some like alpha times C edges crossing the cut. If the minimum cut is of size C and there are I vertices, each vertex must have degree C. I mean, if a vertex has degree less than C, then you should just remove all of those edges. So you have at least I times C over two edges. What's the probability that you pick one of these alpha C guys? It's that number, which has a very nice form to alpha over I. Once you now take this and just take, okay, what's the probability that in all of these steps, I miss this cut C? I didn't pick an edge from this cut, from the cut going from this cut. Well, that probability is exactly this expression, which turns out to simplify that. Okay. So that's the entire proof of the cut counting bound. This is what we want to work with in the coding setting, and we have to ask the question, what's the analogous notion of contraction? What's the analogous notion of the cut counting bound? We'll get to that. But before we get to that, so first, does this proof make sense? Even if the proof doesn't make sense, at the end, what it's giving us is a cut counting bound. The number of cuts which have small number of edges is small. Once you have this, you can immediately get what was original Karger sparsification, which just said, okay, if I have a graph with a large minimum cut size, I can sample it down by a factor of 1 over the cut size. Okay. Why? You can just do the union bound and see that, it's okay. I want to preserve small cuts are more delicate. There are fewer objects to sample from, and they have to be counted correctly, but there are few of them. And so I can do a union bound just like how do you prove expansion of a random deregular graph? I mean, the same kind of, you have to do union bounds, but the small cuts, you have to worry about less. Benczur and Karger sort of came up with a more complicated notion of how to define strengths of edges and so on in order to get from this kind of a cut counting bound, a bound which says, oh, even when the cut size is small. So suppose the cut size in a graph is 1. So let's think of this 2 cliques connected by 1 edge. Cut size is 1. Number of edges that you're starting with is n squared. After you do the sampling and thing, you're still left with n square edges. Nothing happens here. What should you do in that case? That didn't really improve, but Benczur and Karger were able to improve even that case. You have to be more careful. Here is our proof of it, which is, I think, it loses a few log factors, but it's completely modular given what we've seen so far. What are we going to do? So some numbers are being specialized over here, but let me give you an illustrative example. Let's start with this, 2 cuts of, there's 2 cliques and this middle edge. I'm going to look at every cut of size at most square root of n and remove it. Okay, take a cut of size square root of n edges, which will disconnect the graph, remove it. Now I get 2 pieces. Another square root of n size cut here, maybe that splits it further into 2. Another square root of n size cut here, remove it into 2. Keep doing this till I'm done. How many edges did I remove? Well, each time I'm adding the number of connected, 1 to the number of connected components, I can repeat it at most n times. So there are n to the 3 half edges that I've removed. Call that the graph G0. The remaining graphs have some connected components sitting there. In this example of 2 cliques, I would have 2 cliques of size n over 2. But they have a minimum cut size of at least square root of n. Because if it wasn't that, then I would have repeated. Apply the Karger sampling to the left graph. You can sample it down to square root of, n to the 3 half edges. The right graph, just preserve it as it is. You've now taken a graph of size n squared and sampled it down to n to the 3 half edges. And you can repeat this process and get all the way down to nearly linear. You lose logarithmic factors, but that's it. Okay, does it make sense? So really, there's a very simple natural process which says as soon as you have a cut counting bound, and you know that you can sample things down by size of the minimum cut, this is what you should do. You should take your graph, split it into 2 pieces, one which is just all the small minimum cuts, and the other where the minimum cut value is very large. Here you can sample, and here just take all the edges. That's good enough. If you want to repeat, you can sparsify this further and sparsify that further. And okay. So this gives us the sparsification results. And now we'll turn to code sparsification, which is the goal for the question.
So was that procedure you described just now algorithmic?
Good. So what's algorithmic about this procedure or not? I have to find this graph G0. In order to find this graph G0, I need to find the minimum cut in this graph. And minimum cuts can be found. Even before Karger, we knew how to do that. And with Karger, even this random sampling actually naturally finds the minimum, a small cut for you. Okay.
So, Madhu,
Yes.
is the algorithm you described equivalent to some non-uniform sampling? Like, could you somehow produce the same distribution of the outputs for each edge choosing the probability of sampling and?
I think so. Louis is more on top of this thing. What's it?
Yeah, so this is actually, it's kind of like a stochastic perspective on Benczur Karger, because the weights of each edge will actually concentrate to be approximately like the 1 over the strength. So it's like essentially an analog, but it's easier to analyze because it's like stochastic. Okay.
But it's equivalent to leverage score sampling.
Essentially.
Great. Glad there's somebody here who knows the answers to questions. All right, so code sparsification. So the first thing we need is a generalization of this cut counting bound. The analog of a cut in a graph is the minimum weight code word in a code. And so you'd like a result which says, okay, the number of code words whose weight is at most 10 times the weight of the minimum weight code word is polynomial. But this is just patently wrong, right? I mean, there are asymptotically good codes. And what's the property of an asymptotically good code? You have exponentially many code words. And their minimum distance is linear in the length n. So so clearly if I take the minimum distance multiplied by 10, I get all code words and there are exponentially many. So cut counting bound is just patently false in this thing. And this was an obstacle that had been noticed repeatedly, even not exactly maybe in this form, but also in the context of hypergraph sparsification and so on. Something is breaking down. The cut counting bound is simply not true. The thing that saves us is that this is actually not an obstacle to sparsification. If I want to sparsify an asymptotically good error correcting code, I just output the code itself. I already have linearly many rows in the columns, so I'm done, and there's nothing to be done at this stage. So this was not an obstacle to sparsification, but it is one to the cut counting bound. So the counting bound has to change. And this is what we came up with. So roughly what we want to say is that if you're looking at this code C, roughly what's going to happen is there's some subset of these things which might actually form a very good error correcting code. There are lots of code words, but there's very few coordinates that they're supported on. So we will just hold these coordinates and not even try to sample them away. The rest of it, we will sample it away. Okay. That's that's what we would like to be able to do. The formal statement is for every code, you have sort of one of the two things. Either a code word counting bound holds. So if you ask, for every alpha, how many code words have weight alpha times t, where t is any parameter that you choose, that number is at most like q to the, like some polynomial in n and q. So for this talk, just ignore q and focus on the dependence on n. Or there is some code over here, which is supported on very few coordinates, but it's very dense. Okay. The minimum weight code word is one example of this thing. So think of the simplest case where the code has minimum distance less than t. Okay. Then there's one coordinate, one code word. It's a one-dimensional subcode, which is supported on just t coordinates. But our counterexamples may be more general. There may be a two-dimensional subcode supported on 2t coordinates, or a three-dimensional subcode supported on 3t coordinates. Any of these would be considered an obstacle to our cut counting bound, code word counting bound. But once we remove such obstacles, we are left with a code where you have a good counting bound. Okay. Questions at this stage? I think this is a good point too. So either your code is, what happens if your code is asymptotically good? Well, then there will be basically, everything will fit in this thing. So the whole code is actually supported on very few coordinates and it's very dense. On the other hand, if your code is really like very, very, very tall and very skinny, then either it has some subset over here, which is actually, the code words live only on these coordinates and happen to have a lot of density here. Well, if that's the case, don't try to sample these coordinates away because this is going to be very important. Or the rest of them are looking like a nicely smeared random code and you can work with the top. Okay. Why is this useful for sparsification? For sparsification, we will just say, look, take all the coordinates that are in the support of C prime, include them in your sparsification. For the rest of the code, because the counting bound holds, sample. Okay, sample at rate 1/t. And once you put this together, you can just go through the same paradigm that we used for the Karger's counting bound and how to sample it, go through the same process and you'll get it. Okay, does this make sense? So this is the proxy. This is the proxy, I think, that eluded people in the setting of hypergraphs. It may be, I don't know actually, what does this concept of support in dimension really mean in the general hypergraph setting? It's maybe like a dense graph, but dimensionality seems somewhat different. So it's conceivable that this is the reason why it was missed out over there. But in the linear algebra space that we're working with, it's sort of very natural measures, and then this bound seems fairly natural.
You think of T, okay.
Sorry, yeah, go ahead.
No, I think that was the answer to my question. T is a function of n and k. So what's the?
Yeah, I can choose whatever T I want and then ask how many code words are there of weight T. One reason you might find lots of code words of weight T is because T is actually very large and the distance of the code is small. But if T is kind of like the distance of the code, well, there are still some reasons why things might fail because you have, 10 times that distance and suddenly you have a whole good code sitting there. We just put a big code over here and then some other code or some other code, So we want to, T can be any parameter you choose. Either there's like some code that's supported on these few coordinates, or there's not too many code words of weight at most alpha.
There's a few coordinates. If T is like order of k or something, or n, then it will be times. I mean, it's really the dimension times something very large.
Right. Yeah. So what we find here is going to be pretty large. Right. But it's kind of within the sort of, so let's see how to use this for one level of sparsification. So once again, let's pretend k is the dimension of the code that we're looking at. Let's say n is k squared. You're starting off with the k squared rows, k columns. We want to sparsify. We will use T as square root of k. Okay. So the subcode that you will find will have k to the 3/2 rows. So it's smaller than the whole thing. It's reasonable and you can hope to keep the whole thing. The rest of the code has minimum distance at least square root of k. Not only minimum distance at least square root of k, it's actually satisfies the code counting bound with the parameter square root of k. How many code words have weight 10 times square root of k? It's k to the 10. So up there, you can just sample at rate 1 over square root of k, and those coordinates will do a good job. So the top half, which has k squared rows, you sample at rate square root of k and get k to the 3/2. The bottom was net total of k to the 3/2. You put them together, you have a sampler, which is a non-trivial sparsification of whatever you started with. You can apply this for any choice of parameters n and k, and this will always give you sort of square root of n times k as your final size. So you can keep applying this and keep squishing this. Zev, you look confused, which is great. I'm hoping a question is coming.
So this preserves the weight of every code word?
This preserves the weight of every code word. You're doing a union bound over all the code words.
So you sample the...
On the sample coordinates, you've obviously got the right number. On the, sort of the C prime part, the small dimensions that we just decided to store entirely, we're obviously getting the right number because we didn't throw anything away. On the top half, we are sampling, but then there were not too many code words of low weight anyway.
That's just the same union bound as the output.
Exactly. The usual union bound just works. Just have a counting bound, so a union bound works. Great. So, I think we can go a little bit over this code counting bound. So roughly our idea is going to be, try to simulate what the Karger counting bound works like. So you're starting off with, maybe I'll try to do this on the, can I do this on the board? Will it work? Yeah, great. Yeah. So we have this big code and so imagine the first row happens to be the minimum weight code word. Okay. First column is like this. Okay. What we're going to do is the following: pick a random entry which is non-zero. Sorry, random. Let me. Pick a random non-zero row. Okay, so maybe we pick this row, which is randomly and non-zero, and pick a non-zero entry in this row, and just do a sort of a column shift on this operator. So maybe there'll be some couple of other entries which are ones here. I'll just subtract this column off from everybody else. And from now on, I'll just say, okay, let's sort of, remove this one. So this is corresponding to the contraction that was happening in Karger's thing. You picked one coordinate and shrank according to this coordinate. What's left is a code word that's supported on the rest of the rows and has dimension 1 less because I'm sort of taking away this one column. Okay. The chance that the minimum weight code word is going to be sampled over here is very low because it's low weight. I mean, I'm picking a random row. This has only 3 non-zero entries. And so with high probability, I will not pick this one. Okay. So this is the rough idea. And once you have this kind of an idea and you work through the calculations, it sort of works out. And what it will tell us is that if you started with some fixed low weight code word, the probability that you will sort of shrink it away by this process, but the only way I shrink this code word away is by sampling one of the ones in it. If by picking one of the rows corresponding to it is very low. I keep reducing this matrix till I get to the point where it's looking like a very dense matrix. When it's a dense matrix, I stop and say, oh, look, I found a code word which is too dense. And that's sort of one of the two cases. The other case is I keep doing this and I'm sort of done at this stage. I output the one remaining code word that I find. And the claim is that this is going to be the code word that was hidden in our head from the beginning with some non-trivial probability, just like in Karger's counting bound. Okay. So it's an exact argument that's similar to the Karger counting bound, except the ending point is not always that you come down to one code word. At some point, you might come down to an asymptotically good code and you stop there. So, at this stage, I have too many code words, too few coordinates and too many code words. Let's stop now. Report this as a high dimensional dense code that we found.
So the claim is that after you take out the asymptotically good code part, the C prime, what's left has this property of small weight thing?
So that you don't need to prove. Once you have a statement like this lemma, the corollary sort of follows immediately, right? So we're just going to say every code is either of this type or of that type. It either has a dense subcode sitting inside it, or it satisfies the counting bound.
But in the next slide, you do both, right? You take C1 out and you apply the first. So you keep taking out.
Exactly. So now you can keep taking out. So if I found a dense subcode, you take it out. And you find another dense subcode, you take it out. Keep doing this. At the end, you will be left with a code which is on the rest of the guys. There's a counting bound on and the number of coordinates that you removed is the dimension of whatever you remove times t.
What if you keep taking number 2 and you end up with the original code? You didn't sparsify anything.
Because each time you're only removing a few coordinates, right? So I had k-square rows. Each time I'm removing some dimension times square root of k coordinates and losing this dimension in the overall space. I cannot go up to k to the 3. I can only go up to k to the 3/2 this way. I can never get up to k square.
Oh, so it's like you do like a block, you find like a decomposition of the matrix into blocks.
Exactly. So yeah, the decomposition, what does the C prime look like is, well, if you look at the generator matrix, here is where the C prime is being generated. We don't care what's sitting here, but this part is all 0. And the rest of C is probably sitting there and so on.
Unless n was small to begin with.
Exactly, yeah.
So the step you do when you subtract out like the ones is basically one step of Gaussian elimination.
Yeah.
You made like things independent of that column. And so that's why you pay for one dimension only once.
Yeah, what's removed, yeah, okay, this one row that we are removing is being removed just the once, yeah, and then that's reducing there. All right, so, yeah, the details actually, I'm not great with them, but Louis is excellent with them, so ask him questions about it. So I'll take a few minutes to talk about the efficient sparsification, then I think we're more or less done with everything anyway. The bottleneck to making all of this algorithmic is we are more or less solving a minimum distance problem in this process. How do I find this code C prime if it exists? It's a dense subcode. An example of a dense subcode, as we pointed out, is a code word of small weight. If the code has a code word of small weight, you can't find it because that's an NP-hard problem. Okay, so clearly the problem that we want to solve is not equivalent, but in what sense is it more general? It actually eluded us for quite a while. So eventually we realized that there is a sort of a simpler problem that we want to solve, which is you're given some parameters. Sorry, there should have been t corresponding to the previous slides, but I'm given some number d. I think this is the minimum distance of the code. I want to find not the minimum distance, minimum weight code word, but I want to find dn coordinates which will contain this minimum weight code word. Okay, if I can do that, then I'm sort of halfway there. At least I've seen, we don't see the minimum distance as an obstacle. The right thing to do would be to say, oh, and by the way, if there is a 2D dimensional subset of coordinates which contains two independent code words, if there's 2D coordinates which contain two independent code words, or if there's 3D coordinates which contain three independent code words, etc., all of those should be contained in the same ND coordinates that we output. Okay. It still seems as hard as the minimum distance problem, but it is not. And here is a very simple algorithm. All we're going to do is repeatedly do the following. You have this matrix, find a maximally independent subset of the rows in this matrix. Remove them, that's my set S1. Now find a maximally independent subset of rows, remove them, etc., etc. Keep doing this d times. Take the union of these coordinates, this will contain all your low weight counterexamples. That's it. So the algorithm, I mean, if you think about it now, okay, so look, for instance, there was this minimum weight code word sitting here. And I want to say, when I remove the first basis element, I must have removed at least one of these rows. Well, it's obvious, right? I mean, let's write the generator matrix so that this guy is one of the generators. If I'm only sampling rows which are outside, I'm getting, it's not a full dimensional space. I'm missing the space generated by this column. So you must sample one of these rows. And you repeat this d times, you must have sampled all of these. And so there's the algorithm, which was somehow, yeah, I mean, it's very simple in retrospect, but we did miss it entirely. And now everything that we are doing related to this task is now algorithm.
So Madhu, is that DK, or maybe I just forgot the notation?
Sorry. No, D is just any parameter.
Right. But D is supposed to be the distance, right?
Or D is supposed to be like the distance, or I called it T in the previous slides. Yeah, it's the same thing. Yeah, but yeah.
And each time you're like pulling out dimension many elements, right? So it's
I'm pulling out K elements, let's say.
It's D times the dimension.
Right, D times the. Right. Oh, yeah. Okay, sorry. Yeah, this number should be D times K. Right. Yeah. Okay, good. That's a correction. Right. Yeah, so we often work with little n and capital N in our paper, so that's where usually. And the n here is correct. This is the correct n.
Yes. N is like the number of bits in the code word.
Yeah. This thing should have been. Yeah. All right. So like I said earlier, hypergraph sparsification is a sort of a straightforward consequence of this result. You just apply it to a large field, which is not the field of size 2, and then you can get hypergraphs of unbounded arity. They all work and they all get compressed to basically nearly linear size. So previously, people knew that if the hypergraph had bounded arity R, then you had nearly linear sparsifiers. This was improved to nearly linear by work of no, it's Chen Khanna Nagda, is that right? Okay, yeah. And but ours is giving us a sort of a straightforward proof. It's just a corollary of, by just applying, using these as the rows of incidence of the edges. And yeah, we, in order to do this for over general groups and so on, general abelian groups, you sort of stop working over finite fields, which means you can't do linear algebra. but instead you have to do the things that you usually do with lattices and so on, so Hermite interpolation and so on and so forth, and things end up working out quite cleanly. And this is why we are able to classify all symmetric Boolean CSPs, which have nearly linear sparsification. For this it was really important. If you were working with A mod B and B was a prime, then the previous result captured it. But if you're working with A mod B and B is 6, then previous results did not. This one tells us that it does. And yeah, the open questions, I think this is, we're very far from actually classifying all the CSPs which are sparsifiable, especially when you consider sort of arbitrary alphabets. So I want to consider 5 partitions of the vertices of a graph and count the number of edges that go in all 5 of these partitions, or etc., etc. You can ask all kinds of interesting questions over here, hypergraphs and with multiple color classes and so on. You have a rich class of questions that could be asked, and very few of them are known to be analyzed. Anything that is known to be sparsifiable, as far as I know, is sparsifiable based on this polynomial sparsification theorem over here. And it's the lower bound techniques are also kind of very pathetic. You just know that the and is a very unsparsifiable constraint, and so anything that follows from that, these are very far from each other. Try to find new things that new ideas in sparsification would always be very widely appreciated. New lower bounds, I mean, yeah, maybe. All right. Okay, I'll stop there. Thank you.
Questions for Madhu?
Or Louis, actually.
So can you get something interesting for coding theory? Let's say applying this for specific families like Reed-Miller codes or.
Yeah, so I actually never thought about applying it for coding theory questions. And Reed-Miller makes a lot of sense because it's one of those codes where the dimension can be small and the space is pretty large. But at the end, I think our algorithmic results are randomized polynomial time algorithms. They're not deterministic polynomial time algorithms. It's because at the end we say, okay, look, there's some obstacle that's sitting there. We can find it deterministically, algorithmically, and then the rest we will just sample randomly. And that's the part which is probably not thing. So yeah, I mean, it's conceivable that there could be something asked. We've not actually thought about that question. Yeah.
So there's the other direction though is that like a consequence of the code sparsification is that like as you mentioned, you can sparsify the generating set of any Cayley graph over F2. So there could be some opportunity if you want to like optimize the rate of a code if it's using a specific Cayley graph. You can now like sparsify the generating set. But,
right. So if you have a high degree Cayley graph, which is an expander, sparsifying it, you can sparsify just the generating set rather than the graph itself. Sparsifying the generating set will sparsify the graph also in the process, but you get a Cayley graph. And this Cayley graph is a spectral representative of the original graph that you started with. That's a very interesting consequence that.
So that wasn't known before?
This was not known. We only know it now in the context of Cayley graphs over Z2 to the N or something, right? Z2 to the K. We don't even know this over other abelian groups.
But your bounds would lose log of the group size or log square of the group size?
We may lose, so this is not going to be a linear sparsifier. I mean, so it's not a constant degree sparsifier at the end. The numbers that we're counting are sort of in the degree, like the degree goes from some number to something smaller. I don't quite know, what we would lose, but it's.
See, I have a related question. So, you the whole talk was about cut sparsification, but for graphs, there's a stronger notion that implies cut sparsification, like the spectral sparsification. Is there a generalization of spectral sparsification to, I don't know, like more general settings like you looked at, like CSPs, cuts, etc.? CSPs and codes, etc.
We thought a lot about it. As far as I know, we didn't find anything. Did we find a good reason that we didn't find anything?
No, I mean, because hypergraphs have spectra, but somehow there's like XOR is like extremely periodic, right? Like somehow it doesn't make sense that like you put a one here, it'll go up to 1, you put a 1 here, it'll go down to 0, and then it just keeps going up and down between 0 and 1. It didn't really. I mean, maybe there's like a sine function or something that's actually, we didn't, yeah.
So yeah, I mean, it may be an interesting question to ask in the general context of CSPs. So which of these CSPs have a notion of a spectral sparsification? The OR of k things, yes. The AND of k things, yes. But something that's non-monotone and sitting in between, even if it's monotone, do we know anything? I don't know.
I was going to suggest, like, so one way to think about spectral sparsification is that it's a generalization of assignments that you are preserving, the form would be like the value, and then, if you have, as long as you have a way to give value to, some relaxation of the space of assignments, you could imagine like some generalization occurred. And then it's maybe natural to ask SDP value.
Right. So given that, I mean, I don't know. It's conceivable that we could think of a real vector as just a probability distribution over assignments, and then to ask the question, can you now say something about the expected value of the satisfiability? I don't know if, I mean, but I don't, we didn't see a nice way to get a nice result in the setting. I don't think we found a good obstacle either. We were definitely, I mean, given all the extensive work. I mean, also, I think when you think about graphs, do not have just a sparsification of nearly linear size. They have a sparsification of linear size.
Yes.
And as far as I know, the only proof of that is via spectral sparsification. So if we want a linear size, I mean, forget whether we can do a spectral version of code sparsification. I want a linear size representative of coordinates. Can I get it? I don't know how to do that because I don't have the tool. One key tool is missing. So that's, even without this question, so we could just ask what is the extension that would allow us to get to that question? And maybe it will be some way of interpreting spectral sparsification differently.
So I guess that's not even known for hypergraph cuts. I mean, Young, I guess, has thought about.
I see. Okay.
I don't think it's known, yeah.
No. Okay. Good.
I think even like 3 hypergraphs, it's not known.
It's not known. I see.
Like, no, I'm not so sure. Yeah.
Okay, great. Yeah, so like I said, certainly there exist people in this audience who know more about sparsification than I do.
Okay, more questions for Madhu? Okay, let's thank speakers.